All right, so we've got a few people still coming in, but we're going to go ahead and get started because we're a couple minutes past our start time here. But good afternoon. I'd like to welcome everyone to today's SPTC webinar, Past, Present, and Future Trends in Bridge Engineering. Dr. Atorod Azizinamini is with us today to give this presentation. And today's webinar is jointly sponsored by the Southern Plains Transportation Center, Accelerated Bridge Construction University Transportation Center, and the Oklahoma Department of Transportation. My name is Royce Floyd. I'm an associate director of the SPTC, an associate professor in the School of Civil Engineering and Environmental Science here at the University of Oklahoma. And I will be introducing our speaker as well as moderating the question and answer session. So to start with a few housekeeping items before we get to our presentation, please be sure to mute yourself throughout the presentation. I'll also be monitoring that, but if you could help me out, that would be very helpful. And then we will have a Q&A session at the end of the presentation, but feel free to go ahead and submit your questions in the chat so that you don't have to remember them. And I will ask the questions in the chat to the speaker at the end of the presentation. You can also raise your hand when we get to the Q&A session, and I'll ask you to unmute to ask your question. Our presentation today is being recorded, and the recording and the slides will be posted to the SPTC website after today's event. And then you will also receive one PDH for attending today, and those certificates will be sent to the email address you used to register for the webinar in a few days. So finally, please take time to complete the survey that will be sent out to you after the fact, so that we can use that feedback to improve these webinars, as well as if you have any suggested topics that we could get speakers on in the future. All right, so with that, I'll move on to introducing our speaker. Our speaker today is Dr. Atorod Azizinamini, and his presentation is titled, like I said, Past, Present, and Future Trends in Bridge Engineering. And I'm sure he'll tell us a lot about the context of that today. But Dr. Azizinamini is a PE and is the Director of Infrastructure Research and Innovation at Florida International University and is the Vassant Surtee Professor of Civil Engineering. He is also the Director of the Accelerated Bridge Construction University Transportation Center that's headquartered at Florida International University. A majority of his current research activities are related to the development of UHPC-based structural engineering solutions, which include development of permanent UHPC formwork, 3D printing using UHPC, repair and retrofit using UHPC, and complete design of buildings using UHPC. He's led more than 60 million in research as a principal investigator and has published more than 300 technical papers and graduated more than 35 PhD students. He also has received many awards, including President Obama's 2015 White House Champion of Change Transportation Innovator Award that he received in 2015. So with that, I will let Atorod take over. And I know he will have an interesting presentation for us on the past, present, and future of bridge engineering.
All right. Thank you, Royce. Thank you, Royce. And thank you for inviting me to share a few thoughts. You know, actually, I was the last couple of days, you know, that's a life of a, I guess, a university professor. The last couple of weeks, couple of days, I started basically putting my thoughts together. And I said, oh my God, what kind of topic did I select? The past, present, and the future, because there is so much to say. And but I'm gonna do my best, okay, just to share some of the ideas, some of the thoughts that I have on where we have been, where we are, and some comments about about the future, because we have lots of challenges ahead of us, especially with the existing bridges. So with that introduction, let me just go ahead and start. And hopefully you will find something useful in the presentation. And by the way, Royce did a good job to introduce me, but he forgot the most important thing. He didn't say that I got my bachelor degree from University of Oklahoma. So so Royce, next time, please. And so let's go ahead and start. I mean, building basically the bridges goes many 100 years. Sometimes we say, like Ponte de Gard bridge in southern France, I mean, has lasted decades. And sometimes the thought is that, well, we really did a much better job in the past. Well, but don't forget that for every bridge that was constructed decades ago, there is thousands of them that did not stand the test of the time. But nevertheless, the bridge engineering has been fascinating really over times, and lots of innovations. Actually, I kind of admire the innovation that went into the bridge engineering at the time when there was no steel. And so the shape that you see down here, the arch, the reason for that was that at the time there was no material that would take a tension. So they had to use an arch in order, because it resists the compression. And that's why the massive, the size of the structure that you see. And in fact, you see that in the buildings, in the old church, for example, in many churches, Europe, in the Middle East, and so on, the same type of structure, because there was no material that would take a tension. I put this slide over here. I'm pretty sure that some of you are going to say, this Atorod is out of his mind. Why does he have the painting of the Mona Lisa by Leonardo da Vinci? Well, those of you, I think some of you know, Leonardo da Vinci was probably the most famous contemporary, the first contemporary civil engineers of our time. And I remember that I had the opportunity to be in Milan, Italy. And if you go to Milan, Italy, there's a good museum, the works of the Leonardo da Vinci. And when you go and you see he's a Renaissance man, and what he did and the invention that he had is really amazing. And he was he had to make some money. So actually part of during his life, actually he joined he was making a military equipment, coming up with these inventions like a tank that you would go inside of it and hide and then try to fight with the enemy and so on. And there are so many things that is really credited to him. Actually, some people say the bicycle was even invented by Leonardo da Vinci. Some say no. The many things for the under the water, for example, the scuba diving, things like that. I mean, he's got some amazing invention. But one thing that he was for sure was a civil engineer. And in fact, what you see on the top right-hand side of your screen is actually a tension test that Leonardo da Vinci had in order to establish the tensile capacity of the basically the wires. And in the translation, actually, there are some controversy actually about this test, but nevertheless, basically he had this maybe over here, he had this basically the rope, and then there was a basket, and then there was basically the weight would drop from here, and then once the tensile capacity of the rod was exceeded, it would drop into this basically the hole, and that would tell him, and he would repeat this one. Actually, I think he wanted to repeat this test with a different thickness of the wire. In some translation, they say he specified the changing the length of the basically keeping the thickness the same, but changing the length. But from mechanics of it, that should not make a difference, because the stress is a stress and the rupture stress is rupture stress. But I think he meant the thickness, and that was I think the issue with translation. But anyway, so the reason I showed this is because the contemporary civil engineers were really occupied with the strength, and rightfully so. They wanted to make sure that everything had enough strength. For example, the bending test at Galileo, that, for example, they came out. There is a book, very good book on the history of the strength of materials. If you get a chance, read it, and then you will see some really very interesting topics. So our first civil engineers, really, when they were inventing something, they were always worried about worry about basically the strength. Now, people who like John Rublin, who designed the Brooklyn Bridge, actually he was thinking about the basic the service life too, and I will mention that. So, but back then, of course, really we were not worried, and rightfully so. We didn't have the heavy traffic, and we didn't have the and so on. So the early days of the bridge engineering really did not have many parameters that we were concerned right now. Now, one thing I should have mentioned is that so originally everything that the civil engineers basically were inventing, they were worried about the strength. And if you look at the ACI building code, and if you look at for example, let's say the AISC the building code, really there is lots of provisions for a strength. And the reason I'm mentioning that is because many provisions that we have in our AASHTO LRFT bridge design specification and a bridge code really is rooted in the building code, steel and the concrete. For steel and concrete, the strength is fine because every element is protected and you don't have that much durability problem, exposure. But in the case of the bridge, it's something else. So that's a very important thing to consider. One of the reasons that every day seems like we are developing a new AASHTO guide for this, new AASHTO guide for that, is because really we have taken many items from the ACI building code, from AIC building codes, which are really strength, rooted in the strength, but the durability is what really is giving us a hard time, the corrosion and so on. And those are not really addressed through the strength. Those should be addressed through the life cycle performance, the long-term, the cyclic behavior, exposure to the weather element, and so on. But, despite all that, you say, there are some bridges that did last more than 100 years. So I'm going to show you some of them. Well, and I put actually the age over there too. Brooklyn Bridge, 140 years old, right, as of today. But as and this bridge really, it was John Rublin who designed the bridge. Actually, he was a very smart guy, and he used the graphite to protect the steel cables. He thought about that, One side comment, one observation as I look at the past, especially in the case of the bridge engineering or any other really scientific area, you find people that, for example, they are engineers, they are mathematicians, they are philosophers, they are poet, they are painter. I mean, look at the Leonardo da Vinci, Mona Lisa, the painting, but then he thinks about the civil engineering problem. And I think as time passes, we tended to be more specialized in different areas. But some of the old bridge engineers like John Rublin, who designed the Brooklyn Bridge, really, he was thinking outside the box. He was thinking about the head. He knew that the corrosion is going to be problematic. So he used the graphite, and that protection lasted a very, very long time. And then we have Williamsburg Bridge that was not really maintained. I should also say that one of the things that you will notice, for example, in the Brooklyn Bridge, the maintenance. I mean, the maintenance that has gone into the Brooklyn Bridge over the years is, because of its historical landmark, basically is phenomenal. And so as the New York really has done a wonderful job in maintaining some of these bridges. The Williamsburg Bridge was not really as maintained, and I think it was 1988 they had to close it, and then in fact they were trying to see that what they should do, and finally in November of 1988 they decided, a group that got together and decided that after they closed it in I believe October of the 1988, they were trying to see that whether they should replace the Williamsburg Bridge or they should continue. And the decision was that because of its historical landmark to go ahead and rehab. And I believe 1991, the major rehab started. Now, one of the items really for this bridge that really catches your eyes is the fact that these cables, they were originally designed with a very large factor of safety. If I'm not mistaken, I believe factor of safety was about 5. But over the time, the factor of safety decreased. But still, it was good enough to serve the type of the traffic that nowadays it has. So that's another lesson that one of the reasons, other than the maintenance and then the rehab, is really the very high the safety factor that went into design of for example, some of these bridges, like a Williamsburg Bridge, that had a safety factor of 5 for the cables. Over time, it decreased, but let's say 2.5, 3, but it still is good enough to meet the current criteria. Another bridge, for example, that have lasted very long time. This one actually is a very interesting one. San Luis Edge Bridge. This one also was closed at a time. And when it was designed, the top was the top level was pedestrian, and then there was a railway in the bottom, in the lower level, basically over here there was a railway, and one of the really interesting aspect of this was, first of all, the center span was like 500 feet, was 200 feet longer than any other bridge of the time, and then the other aspect of this one was that actually the construction of this thing used the cantilever method without any temporary shore. So that's another feature. The other aspect, actually, when I was looking at this picture, it struck me both with respect to the Brooklyn Bridge and the San Luis, the Edge Bridge. And by the way, Edge is basically the designer, and that's why they named it after the bridge after the designer. I think another reason is the very heavy substructure that you see down here, very stocky. I think that also had to do something with the fact that these bridges have lasted so long. So anyway, so we do have bridges that have lasted a long time. But if you look at it, really the couple of things jumps out. One is that the reason that they have lasted more than 100 years is that they have maintainable and well maintained over their 100-year service life. It's not without the maintenance. So the maintenance really plays a big role. The other thing is that it's been adaptable to changing function, use, as well as the service limited state demands. And because of basically the size and the weight and so on. And finally, originally over-designed, just like a Williamsburg Bridge that I mentioned, that the safety factor originally for the cable was 5, but then over time it decreased. Now, the designer did not do a good job in protecting the cables. In the case of the Williamsburg Bridge, like Brooklyn Bridge, John Rublin used the graphite, but they used I think some type of oil for the Williamsburg Bridge. But these are some of the three, really, if you want to identify why some of the bridges that we have that have lasted 100 years, those are the reasons, basically. The other thing that in the past, actually, I said the history repeats itself. If you ever think that the accelerated bridge construction was invented by us, think twice. I think some of you probably know, back in the old days, before having a proprietary bridge system being a no-no, I'll elaborate on that in a minute. You used to actually, back in the old days, there were these salespeople that they would go from the county to the county, and they had these catalogs. And then they would go to these counties, and then they would show them the pictures of basically these bridges, and then they say, okay, which bridge do you want? For example, this one right here, this one out of a catalog. I took this from a publication by the Texas DOT, actually, and this is actual bridge, okay? And this is how it works, basically. The sales people basically would come, you would look at the catalog like a Sears catalog, you would decide what you want. They would take your order. They would go to the company. There were some companies in Ohio, the Pittsburgh, mainly in the Midwest and the East Coast. And then they would ship it. They would ship the parts, basically, and then they would assemble it for you. And here is actually one of the fabrication shop where the bridge elements where the truss was being fabricated. One side item really is, if you look at the old history of the bridge engineering, you see that there are so many patents that was issued back in the, Warren Truss, Pratt Truss. These are people that they invented these systems, and they put their name on it, and they were selling them, and it was not a problem. I believe there was a law that was passed in 1975. I don't know what the name of the law was, but I know there was a law that passed that really put the end into the innovations. You look at the number of the innovations that has gone into the phone system. Today we have, for example, let's say I have a cell phone, but there is more than I don't know, maybe close to 800, 900 patent on the cell phone, basically the phones, and that's how it evolves. Basically, with the patent, there is improvement that comes in and so on. But in the case of the bridge, really, we decided in 1975 that we don't want a proprietary item. That's I think where the innovation really stopped. But fortunately, a couple of years ago, Federal Highway Administration actually issued a memorandum that said the proprietary products are allowed to be used in the bridge engineering. But it is not up to the Federal Highway Administration to basically approve it or disapprove it. It's up to the states. So now the ball is in the court of the states. Okay. So I think the morale of the story is that the reason early days of the bridge engineering that we had so many advances was really because of this innovation. There was an incentive for people to invent different systems and put their name on it and then go ahead and sell it and so on. And I think, like I said, fortunately, a couple of years ago, I think it was maybe 2 years ago or last year, a memorandum by Federal Highway Administration was issued, and the states were told that now they can use a proprietary item. So, but it's their decision, okay? And I think innovation is we do need that, especially right now, because there is so many new technologies are being introduced into our system. Okay. Now, back in the old days, of course, we didn't have many challenges that we have right now. And one of our biggest, I would say, the challenge is our existing bridge inventory. That is if you just look at it, I just took this data from over the 30-year period from 1975 to 2005. Okay, that lifespan. Look at what happened. During that time period, the population increased by 32%. The number of the drivers increased by 63%. The number of the vehicles increased by 90%. The miles traveled increased by that much. The weight that is put on our bridges, the one that we know of, not the illegal ones, the legal ones that we know of, is a 400% increase. And how many miles did we add to the system? 6%. So what that means that we are asking our bridges we are putting more and more demand on our bridges. The other thing, I think all of you know, out of that, look at over here. In 2010, we have about 607,000 bridges in our inventory, right? Out of that, by 2010, about 200,000 of them were past their design age of 50. Now, there is a difference between design life and the service life, okay? Design life is over the time that we expect the type of the traffic that we have designed, the weight of the trucks that we have designed to pass over our bridge. Service life is a number of the years that the bridge will continue to function as the system. Now, some of its components may not last that much. You have to replace. But as a system, we say, okay, it's got so much. So there's a difference between service life and a design life. Okay. Nevertheless, design life, when you exceed the design life, I mean, that's a red flag. By 2030, just 7 years from now, 400,000 out of 607,000 bridges that we have are going to exceed their 50-year service life. Now, they're going to require replacement. They're going to require rehab. I think that preservations, the rehab, I think there's going to be more activity in that area because there's no money. Just look at right now the debate on the debt ceiling. I mean, they're trying to, in the Congress, they're trying to cut the spending and so. So there's going to be less and less money available. So we are, on one hand, we are facing with increased number of the bridges. That's going to require rehabilitation, and so on. And on the other hand, we are looking at the massive amount of the constructions and the lack of the money that's there. And if we try to do all this construction type during basically the as usual, I mean, that is going to be problematic because the safety, because interruption to traffic, the mobility and all that stuff is really is a factor. And this is not just for the rural, this is not just for the urban areas. If you think that only this is a problem, the construction interrupting the traffic is only the big city problem, that is not. Even in a small city, because those in a small cities, like Norman, I remember, if I'm still remember, there was a Lenzie Street, right? I think there was a 2-lane, very narrow. Now, if you try to have a construction activity there, to see what kind of traffic you're going to get. You probably have a traffic right now. Okay. So these are another challenge. You cannot just do business as usual. Of course, the service life and all that stuff. I mean, we've got bridge deck is the #1 maintenance problem that we have. Okay. Safety again. The safety really is a big item. If you look at the US DOT strategic plan, and the number is basically the zero fatality. Zero fatality. They don't say. I mean, people assume that they only mean the traffic, the type of the traffic, basically the accident. Well, if you have a construction activity, that's a magnet for the accident too. So the zero fatality of which is the #1 really objective for the US DOT, really applies to the bridge engineering as well. And what that means that if you are aware of a technology or a solution that is going to reduce the number of the construction days, then you got to use it. Again, remember, if you would please read it one more time. Go to the AASHTO LRFT bridge design specifications. I think chapter 2, section, I don't know, 2.5, something like that. The first thing that AASHTO LRFT bridge design specification says is that the primary job of a designer is the safety. They don't say economy. They don't say that you have to develop an economic bridge. It's a safety. It's a safety that really, as a bridge engineer, that we have to be very mindful of that. And nowadays, fortunately, we are also service life. Service life is very important. I put this on because back in the 2007, we got a project we had a very big team, but I don't know, my God, 12, 15 co-principal investigator, and I was leading that project. This was one of the strategic highway research program, Sharp 2 projects. And our task was to develop the methodology so that the bridges last 100 years plus. What really, one of the conclusions that I had, was I always, when I teach a class, I tell my student, I say, if I give you a beam, and I say, I put so much load in the middle of it, support at a 2 and 3 point bending. and give me what is the stress at the top and the bottom fiber. You will use the MC over I equation. You can plug in the numbers and you can give me the answer before I know it. But if I give you the same beam that made of concrete and say, okay, I'm going to salt it. Let's say once a month during the winter time, and let me know when the corrosion is going to start. Very few probably is going to know what to do with it. Or I have a Teflon sheet for the sliding surface. Tell me how long that the sliding surface is going to last. When do I need to go back and then replace that? There, I think you're going to find out that not many people know what to do with that. So we do a wonderful job with respect to the strength again. Remember that the first slide that I had. But when it comes to the service life, we have lots of criteria, lots of rules. So we do that, but quantitatively, we have a very few tools that will tell us quantitatively what the service life of each component is, similar to the way that we do with respect to the stress and the load. But we are getting there. The other thing with respect to the challenges that we have with the bridge, the cost of the replacing a bridge itself sometimes is nothing compared to economic impact that is going to have. As an example, I'll give you one example. This particular bridge is, I believe, it's in Boston, located, and it's a. If this bridge, it's one of those bridges that is rotating to obtain to allow basically the ship to pass underneath of it. This bridge, if it's closed, basically, I think right now it's either just the last year or so, I think the money became available to replace it. I don't know what the status right now is, but it has a very, big history of it. Okay, I'll try to get the name of it and I'll pass it on. I apologize, I forgot the name of it, but it really affects the traffic from the New York all the way to the Washington, D.C., because people communicate from New York to Washington, D.C., and they had to pass through this bridge. So the value of this particular bridge compared to if it was, and it has happened so many times when it was in operation. Again, I don't know exactly. I believe last year the money, it took them many years to come up with the money to replace. And I believe last year they started the construction. So I don't know the current status of it. But when it was before that, when it was in the operation, there was many accidents. There was a fire, actually. There was a fire on the bridge. There were many times that this thing would rotate, and they wouldn't close completely. And that would shut down the train traffics. So people who are commuting from the New York to Washington, they had to wait. So, and that's another thing. The initial, really, the cost of the replacement of this thing sometimes is nothing compared to economic impact of it. So whatever that we can do in order to expedite the construction, repair, and all that, really, if you look at the cost in society, is significant. But the good news is that we have tools. It's good, but we have to be careful too at the same time. I'm gonna show you some of the tools that we have currently. Okay. I mean, we have the capability to really build whatever that we think that, for example, a design concept that we have, and put it to the test, even for seismic. For example, this is a test that at the University of Nevada. As you can, I'm sorry, let me. So this is a shake table test at the University of Nevada, Reno. This is another shake table test that I think it was done back in 2018, and I went to University of Nevada, Reno. We came up with the system called Simple for Dead Load, Continuous for Live Load, and then we extended this application to the seismic region, and then we designed the connection, basically how to connect the girders over here, and then finally we did the basically shake table test for seismic regions. So we have the tools that we can. This is a 1/3 scale model of it, and we subject it to 2.5 times the maximum credible earthquake that this bridge would have seen. And I can show you some footage.
2.25 times the design earthquake.
Here they are getting ready to test it.
225% of the design.
I believe this was they used the drum motion, Stellmeyer, I believe. So we have the tools. Also, nowadays we have high performance steel. New materials are coming to the market. And in fact, there's more other, the ultra performance concrete and so on. In fact, there is even more materials. So we are in our toolbox. Now we have many tools, advanced materials, ultra performance concrete. I mean, this is a few years ago, I believe in 2018, I know because before, I know it was before the pandemic. So I went to Switzerland and visited with my good friend Eugene Bruweiler, and then he showed me some of the applications that they have with the ultra performance concrete on the rehab. So they have taken it. They don't call it rehab; they say upgrade of structures, because when you use a ultra performance concrete to wrap a structural element with the UHPC, you wind up with a structure that is even better than the original. Not only you protect it against the corrosion, but it also adds significantly to the strength. So these are some examples of it. That this is really wonderful material, I think. Or this is a test that we did. We actually put a T-beam made of concrete, and then we added some reinforcement. We put it inside the epoxy glass formwork because we wanted to see how the UHPC flows around it. And you can see over here, see how well it is flowing. And there is this is the bottom of the T-beam. See how it's just smooth. In fact, after we removed the epoxy glass from this, it was like a glass because we use the epoxy glass for the formwork. And so this ultra performance concrete doesn't have aggregate, flows into a very small spaces, 1/2 inch, 1 inch, and you can wrap your deficient bridge elements with the UHPC, and you can get the product that's much better than the original concept. Or nowadays, for example, we are using a shotcrete. So you guys have used the, you're familiar with the shotcrete. This is one of the experiments that we did at SPTC-OU. Basically, with the hose, you just spray it. Or we have, for example, we have developed techniques for timber piles. So what we are doing now, it's much involved than this, but for example, the timber pile that has a 345 kips capacity, we wrap it very thin layer of a UHPC, and then all of a sudden we go to 600, 700 kips capacity. If we add a little bit of a steel in there too. So we've got these kind of tools. And then on top of that, right now you see, for example, robotic construction. Robotic construction really is coming up quite well right now. And this is just to show you, for example, the column that you see right here on the right-hand side, it's printed by the printer. It's a hollow column. If you look at the inside, is this. Now let me show you the printer. This is the printer, comes from the top. Now this is a simple shape. Now we are at the point that we can print almost anything, any shape that you want, we can print. This is one of the simpler ones actually. So if you have a bridge that has several hundred columns that you want to use, and you can print these columns 24 hours a day, and printers don't ask for overtime. So you've got this kind of technology that is coming. This technology are at its infancy, but I think you're going to see over the next decade or so, you're going to see more widespread use of this one. So in summary, really, we have many different type of technology with respect to the analysis and so on. that we can use. And we need to take advantage of it. So in this slide, you know what I did? I said, you know, we have all these challenges, okay? The durability challenges, the dealing with the construction on the left-hand side, basically the first column, dealing with the constructions and the mobility that's going to cause, and the safety problems. Now, there is also what makes the trying to see what is the best way to move forward is some of the disruptive technologies that are coming on board, okay, that we don't know what the impact is. For example, autonomous cars. If everything flows in an autonomous way, maybe you don't need to have a 6-lane, 8-lane highways anymore. If a trucks can go in 1 lane, for example, in certain locations, you don't need maybe that much, but you need maybe a much stronger beam element. Drones, I just put it over here, okay? If you go and Google, in fact, there are a couple of companies that, in fact, you can buy their share actually, that they are developing a drone taxi that you can go from point A to point B. Don't be surprised. Now, this is not going to solve all our problems. I mean, maybe they can address 10, 15% of the traffic problems. For example, if you want to go in New York, you're going to go from one airport to another airport or things like that. So there are some technology that's coming. And what makes our job is a little bit different. You know, what should be the shape of the bridge in the future? 100 years, let me pose this question. 100 years from now, what is going to be the demand on the type of the bridges that we have? I don't know the answer. You may know. I think you may be smarter than I am, and you may know. But I think these are some of the questions that we have to really address. I mean, Ed's Bridge, you know, Ed's Bridge, the one that I showed you in San Luis, originally it was designed for having a pedestrian, basically, capability at the top and the railway in the lower floor, but then it changed actually later after they fixed it. There was a traffic on the top and then the railway in the middle. So the function changes, okay? And I think we have to be able to adapt to the change to possible. We have to kind of anticipate what the changes maybe is coming in the future and kind of incorporate that in our design, in our vision, in our conceptual. And then, of course, there are lots of technology that are coming, artificial intelligence, advanced sensors, monitoring, advanced construction, like accelerated bridge construction, things like that. So these are the tools that we have on the right-hand side. The middle one is the unknown disruptive factors, technologies that are being introduced on a daily basis into our bridge system. And on the left side, basically, we have the problems that we have to deal with. So we have to put all these things together in envisioning what we are trying to do. The other thing that I think it's important, and in fact, we just in February of the 2023, we did get, we were selected by US DOT to have a university transportation center devoted to bringing the latest technology into the bridge engineering and making sure that the bridge engineering in the US is absolutely #1. Innovative bridge technology / accelerated bridge construction - University Transportation Center, IBT / ABC-UTC. In fact, University of Oklahoma is, I'm very proud to say, University of Oklahoma is one of our partner universities in the IBT / ABC-UTC. So we are going to be more working more with the folks at the OU, with Musharraf and the Royce and other faculties. And hopefully they will invite me to one Saturday that there is Oklahoma has a game, so I can visit my Sooners Nation. One of the things I think that we are going to be undertaking is that we need to develop the next generation of the bridge asset management system. You know, there are companies right now in Europe, actually, this photo that I showed you over here, I took it from a company that is actually doing some limited work in the area of the advanced method of the assessing and evaluating the bridges. We need to have the next generation of the bridge asset management system that incorporates all these new technologies that we have, artificial intelligence, advanced sensoring method, and advanced decision-making process. So those are some of the technology that needs to be incorporated. And as a side note, I put this, in fact, just a few days ago, I mean, I had the presentation at the Atorod Cubs meeting in Kansas City, and I told them that at IBT, at our new University Transportation Center, we are going to be looking at developing the next generation of the bridge asset management system. And if at this point we are collecting basically anyone who would like to be a member of the ad hoc advisory research panel for this project, to send me an email. So my email is very simple: aazizina@fiu.edu. And so, but the individuals that would like to work with us have to have a significant responsibility with respect to the asset management system. So, but nevertheless, it's going to take us probably 4 or 5 years to get the first version of it that includes all the technologies that you can think of. And also, I would like to leave you also with this thought. Okay, I think some people are thinking. Take a look at the AASHTO design specification. We had the allowable stress design, right? And then Canadian really in the 70s came up with the load resistance factor design. And then in 80s, a group of engineers gathered in the US and they said, it's time for us to develop a load resistance factor design specification. And it took really, but 20 years or so before AASHTO LRFT bridge design specification really became well accepted with all the state DOTs, little by little. But it was a step forward. And the standard specification is no longer maintained, which is allowable stress design, and nobody is using it anymore. Okay. I think with all these new technologies that are being introduced, I think it's time to take the steps into developing the next generation of the bridge design and construction specifications. I think it's very timely because we are seeing, I mean, new materials being introduced. We are using shapes that are not just I shape or box shape. I mean, AASHTO LRFT bridge design specification, if you look at it, other than the chapters, let's say 1, 2, 3, 4, basically chapter 5 and 6, which is a concrete and a steel, we mainly dealing with the I shape and a box shape, mainly, right? I think we need to allow the people to think outside the box. It should be a standard specification that really provides a general guidelines, takes advantage of the changes that we have seen, new materials and so on, and take a step into development of it. This thing is not gonna happen overnight. Okay, development of the next generation of the bridge design and construction, or the next generation of the AASHTO design and construction specification. I mean, if you look at it, every day it seems like we are coming out with a guide for design for service life, because it was not considered originally in the AASHTO LRFT bridge design specification. So we have a guide. There's a good friend of mine, Habib Dagger, developed a bridge on a backpack, so-called. That's an arch with the FRP. So they had to develop a guide for such a design. Or let's say, for example, we had the folded plate steel bridge system. So now you have to prove that everything is according to the AASHTO LRFT bridge design specification. So that's why I think this is a people who will think, I think people who are going to lead this effort, I think they're going to be remembered for the generations to come, that they were the pioneer to start an initiative that is really changed our bridge engineering practice. And I hope among those of you who are listening today, there is a initiate that thought process. The other thing I would like to mention, if you have not looked at it, there is a document that is called USDOT Research, Development, and Technology Strategic Plan, 2022-2026. USDOT Research, Development, and Technology Strategic Plan. If you have not taken a look at, Google it, take a look at it. There are many, many new ideas. USDOT is looking at the future of the bridge engineering completely different than what we have nowadays. So in conclusion, this is my last slide. I hope I did not bore you to death, okay? I think given the number of the innovative technologies that have emerged in recent years, couple that with the challenges we have with existing bridges, we have an opportunity to hand next generations bridge system that will be lasting as long as we use roads to travel. I don't know how long we're going to be using. Maybe like Mr. Stark, we're going to be beaming the people from point A to point B, but I don't know about the future of that. But nevertheless, we have the opportunity, we have the technology, we just have to take advantage of it. So with that, I'd like to conclude my presentation.
All right, thank you, Atorod, for that interesting presentation, taking us back through history to the future that might be much different than what we have today. I did mean to say that you were an OU alum and mention your love for OU football, but our technical difficulties threw me off a little bit there.
Okay.
We do have a couple of questions that came in during the presentation. If anybody else has questions, if you would either put those in the chat box or the Q&A box or raise your hand, we'll let you unmute and ask those questions. But to get us started off, a question that came in during the presentation was, if you were to identify 3 of the most important research topics or research needs related to your presentation, what would those be?
I would say those topics are, I think, ultra high performance concrete, advanced materials. I think that's, we need more understanding of it, and the UHPC based solution. I think we need to come up with a new bridge system that better takes advantage of those material. That's another topic. And lastly, I think the service life, we need to more systematically trying to address the service life. And then we also have like I said, we are starting a process, and if anyone is interested, which is we are developing the next generation of the bridge asset management system. I think incorporating all these technologies into it. There are more than that. I mean, stuff that I mentioned, I think this will be the other topic that is, I think it's going to pick up more steam, is the development of the next generation of the AASHTO LRFD. And like I said, people who will take that initiative will be remembered by generations to come as a pioneer in this area.
Excellent, thank you. So another question that came in during the presentation was, when do you think that 3D printing of bridge elements or entire bridges may be achieved in practice?
Yeah, you know, in 2019, I remember we had a conference, and I said, within the next decade, you're going to be able to print elements of the bridge on site. Now we are printing columns using a UHPC. We are printing a shell. So the formworks, actually, we are printing a formwork. Rather than making a formworks out of the wood, we are making it out of the ultra high performance concrete. So you can take this formwork to the site, put the steel cage inside, fill it with the concrete. The answer to your question, I think it's going to be faster than what we think.
So kind of following up on that, what do you see as some challenges to that type of implementation?
I think the challenges comes in from you. First of all, you need a workforce that is trained with this technology. I think the constructing what we are finding out is a constructing of the printer is not that much. In fact, all the printers that I showed you, we are building everything from the scratch ourselves. There is no printer that we are buying. Remember, there is a people are right now are printing homes. So there is no reason why we cannot print bridge. There has been printed bridge, for example, let's say in Netherlands have used. Now, I think these are the first generation of the printing. I think it's going to improve when it becomes a more economical. I think it's gonna catch on. The other thing is that, for example, let's say it's not just printing with the concrete. You can print with a metal, which is really like a welding, depositing welding. You can, for example, one concept, you can print let's say you have a truss bridge. You can print all the joint area with a metal, bring it to the side, and then just bolt the horizontal and the vertical elements together. So that technology is here right now. So I think, like anything else, bridge industry, and rightfully so, is a bit more conservative compared to the building in industry. So I think, which is good, because technology have to mature before it finds itself into the bridge market. I cannot give you a time limit, but I can tell you that we have progressed so fast, and we have done so much over the just last 2 years.
All right, very good. So another question, kind of changing directions a little bit, that came in was, I've heard a lot about climate change affecting bridge design lately. What are your thoughts on how climate change could affect bridge design?
Yeah, it's a good question. In Miami area, we are a ground zero for the sea level rise and for sea level rise, actually. And what we are seeing right now, I mean, I'll give you a couple of challenges. The sea level rise is rising. Believe it or not, one of the problems that in some area they are facing is some of these rich people that they have these boats, they cannot go underneath of it, and so they're looking at the raising some of these bridges. But I think when the climate change, the sea level rise that accompanies the sea level rise is not just changing the water level. Also, the pH of the water changes, and the corrosion can start much faster. So being proactive and protecting these bridge columns that are in the water, especially with respect to the splash zone, are very important. Now, the climate change also in the other areas, I mean, we are seeing more frequency of the other drought, or we will see a more frequency of the storms. Okay. And like in the East Coast, I can tell you that it's more flooding. We are seeing more flooding, more intense, the hurricanes, and the more frequency. So all that we have to think about that. The other aspect of it, for example, I can tell you about for example, problems that we have in the Florida area. With respect to the climate change, actually, we need to be very cognizant when we decide, for example, how we spend the money on the bridges, because with the climate change, like I said, the storms and the hurricane season is getting longer and longer, and lots of flooding. So when you try to make a decision that which bridge I'm going to be working on, you better use the ABC if you're close to the hurricane season, because there's only two roads to evacuate the people from the south to the north. Evacuating 2 million people in a very short time, if a category 5, now we are looking at category 6 actually, hurricanes. And it's very problematic. So you have to do things fast. Bridges that are in the of high importance, you have to address them using the latest technology, being proactive, and whatever that needs to be done, you got to do it faster. So in that respect, I mean, the climate change comes in. The other thing that I need to, maybe this was not asked, USDOT is asking now, actually, they're saying that in decision making, we need to bring resiliency, which means that if you have a natural event, you have to be able, the structures have to be able to come back to operation in a very short time. The best way to do that, for the resiliency is start with the resilient bridges. Start with something that is not going to be prone to the corrosion due to the sea level rise. Okay, so you don't have that, because once the damage is inflicted, it takes a time to repair it. So the resiliency really starts with having a bridge structure that is resilient. They're also asking about the equity, the social equity and everything else. When we say equity, that goes beyond just the race and so on. It's a much wider aspect. So decision-making process that we have now has to be, whatever that we decide, have to incorporate these things: resiliency, climate change in your area, whatever the natural phenomenon that is. You are in Oklahoma, I don't know what you call, it's not a natural earthquakes or whatever it is, it's a shaking, let's say.
Or the induced
So you have
earthquakes.
induced, okay, is that the right political terminology? Induced earthquakes, okay,
We'll say so.
so okay, good, I accept that. So you have to incorporate that. That's a resilient. So you cannot say, well, I'm going to wait and see that how long it's going to take before my column is damaged, and I'll go back and fix it. You have to do it before that. So those are the decisions that actually USDOT now is really enforcing, that we have to consider them in our decision-making process.
Okay, excellent. Any other questions out there that I have missed in looking through the ones that have come in? All right, so I think with that, that's all the questions
right.
that I've seen. Thanks again, Atorod, for speaking today. We really appreciate your time. We appreciate your expertise. And it's a great presentation, a lot of important issues. I think Dr. Zaman is going to come on now and tell us a little bit about our next webinar.
First of all, I also would like to echo, for thanking Atorod for the excellent and very informed presentation. And we will see when and how we can get a football ticket for you, Atorod. We really appreciate your love for the OU football team.
All right.
So our next webinar is going to be on June 7th, Wednesday, and it will be given by Danny Gerhardt. He's the Deputy Director of Engineering at Asphalt Institute. And the topic is longitudinal joints in asphalt pavements, best practices. So Danny actually speaks nationally, and that's what he does for a living. And he's going to do it for free for SPTC. And also, as Atorod indicated, that University of Oklahoma is a member of the ABC-UTC. So I think a lot of our events are actually joint events between SPTC and the FIU center there. So, and also I would like to ask you, the audience, I still see that you have quite a few people attending. If you would like for us to cover any topic, we are not going to ask for any money. We might later on, okay? But for now, would you suggest a topic that you would like to actually want us to address? And also the person that if you see that X, Y, or Z, you would really like to have a webinar, we would make sure that we give it a try. So please just throw in your ideas anytime you have a minute. So thank you all again, and thanks to all of you.
Royce,
Yes, sir.
I have a comment, and that is that I feel like you guys need to run a background check. I noticed some characters in this bunch, like John Northrop, Walt Peters, Jim Smith, Audie, and these people. I think you kind of need to vet these people before let them in. That's just my feeling.
Those are important names, Mo.
Well, thank you. I feel like we did have a great audience today, and thank you all very much for attending.
Thank you.
Well, very good. Appreciate it.
So we'll hopefully see you all on June 7th.
Absolutely.